Okay, so I think we can start with the Bayesian part of today's module. Okay, so remember the framework that we summarized this morning about Bayesian model comparison. And let me emphasize the two main issues in Bayesian graphical model comparison. The first one that we mentioned this morning is to design priors for the model parameter that satisfy the constraints imposed by the graph. Okay, so for example, the 0 entries in the precision matrix or the 0 entries in the matrix of regression coefficients for DAGs. Okay, the second issue instead is related to the space of graphs that we would like to explore, okay, to search over using some kind of Markov chain Monte Carlo approach in the Bayesian context, which grows exponentially in the number of variables. Okay, so both for the case of DAGs or undirected graphs. Okay, so we cannot do an exhaustive enumeration of all graphs. This is unfeasible. So we need to approximate the posterior over the space of graphs. Okay, and I will start from the issue number 2 by showing you a very general Markov chain Monte Carlo scheme that then can be specialized to both undirected or directed graphs. And this is the, let's say, easiest thing that you can conceive. Then we will also discuss some possible extensions or improvements. Okay, so it is a very general and simple scheme for Bayesian inference. Okay, so how can we set up a Markov chain Monte Carlo method for structured learning? Okay, so the target is the posterior distribution over the space of graphs G, which can be the space of DAGs or the space of undirected graphs. Okay, so without loss of generality, I will talk about a space of graphs that then we can specialize. Okay, and this posterior distribution is, as we know, proportional to the product between the marginal likelihood and the prior on model graph, in this case, G. Okay. Okay, so as we said, we cannot compute exactly this posterior probability, okay, because we don't have the normalizing constant, okay, which would require a sum over all possible graphs that we cannot easily enumerate. Okay, so we would like to approximate this quantity. And one possible solution is to use a Metropolis-Hastings scheme, so an MCMC approach based on acceptance rejection. Okay, so I guess you are all familiar with Metropolis-Hastings for Bayesian inference. Yes. Okay. Okay. So if we want to design a Metropolis-Hastings scheme, the first thing that we need to structure is a proposal distribution, okay, over the space of graphs. Okay. So something which determines the transition from one graph to another one. Okay. So basically, this is a sort of Markov chain over the space of graphs. Okay. And then whenever we propose a graph, okay, from this proposal distribution, we will need to decide whether to accept or reject the proposed graph. And this will occur with some t, which is given by the usual acceptance probability of a Metropolis-Hastings scheme. Okay. Okay, so if you remember the Metropolis-Hastings scheme, this acceptance probability is basically the product of three components. Okay, the first one is a ratio of, in our case, marginal likelihoods. Okay, so the evidence provided by your data in favor of the graph, the proposed graph that I call G prime over the current graph G. Okay, so this is the marginal likelihood ratio. Okay, the second component in our acceptance ratio is the ratio of prior probabilities, okay, in favor of the proposed graph G prime and the current graph. And then we have the ratio of proposal, which is given by Q of G given G prime. So the transition probability from G prime to G over the probability of transition from G to G prime. Okay, and this is the proposal ratio. Okay, so finally, we will accept the proposed graph G prime with a probability, say alpha, which is given by the minimum between 1 and the Metropolis-Hastings ratio. Okay, so basically, if the the ratio is greater than 1, we accept with probability 1. Otherwise, there is a probability to accept or not what we propose. Okay, so in the first case, we move. Otherwise, we stay at the current graph. Okay, and there is no update. Okay. So in order to compute this acceptance probability, we will need in general an expression for the marginal likelihood that we will need to specialize to Gaussian graphical models. We will need a prior distribution, okay, a prior ratio. This is not easy to specify. And then we will need to compute a ratio of proposal distributions. Okay, so the transition probability from a graph to another one, okay, which is specific of the proposal distribution that we will design over the space of graphs. Okay, so suppose that we have a graph G, which is the current graph. So in order to build the proposal distribution, what we can do, similarly as in the hill climbing method, okay, is to consider a local move from G prime, which can be obtained by insertion, so addition, deletion, so let's say removal of single edges in the graph. Okay, so we can decide whether to add or remove an edge from the current graph. Okay, so if we can construct the set of all possible graphs that we can obtain by applying one of these moves, so there are many edges that I can introduce, that I can insert, and many edges that I can remove from a graph, what I obtain is a set of say adjacent graph that I can reach by applying one of these local moves. So let me call this O of G. Okay, are all the graphs that I can reach by applying a local move starting from the current graph G. Okay, so now what I can do is to draw uniformly a graph G prime from this set of graphs O, which means that the probability of transition from G to G prime, so Q of G prime given G, is equal to 1 over the number of adjacent graphs. Okay, they all have the same probability. Okay, I draw uniformly, so 1 over their number will give me the probability of transition from G to G prime. Okay, so I propose one of these with this probability, and then I will decide whether to accept or reject the proposed graph with the probability given by alpha that we wrote before. Is it clear? Yes? Okay, so this is the idea in this very general MCMC scheme. Okay, now, before moving to the marginal likelihood computation, let me just mention possible choices for a prior on a graph. Okay, there are several different possible choices. Okay, here I mentioned 3 possible choices. The first one is the easiest one. I may consider all possible graphs as equally likely, in which case the prior on G is uniform. Okay, so I assign equal probabilities to all the graphs, and then the prior ratio P of G prime over P of G will be equal to 1. Okay. Okay, so this is a possible choice, but it does not favor sparsity in the graph. If you want to encourage sparsity, okay, you may want to favor graphs with a small number of edges. Okay, so assign a higher probability to graphs with a moderate or small number of links. Okay, so one possibility to achieve this is to structure a sort of binomial prior controlling for the number of edges in the graphs. Okay, so a binomial type of prior can be structured as follows. If we start from the adjacency matrix of a graph, let me call this capital A, then what we can do is to consider the UV element of this adjacency matrix, and this element is 0 or 1, right? 0 if there is no edge, 1 if there is an edge. Okay, let me assume for simplicity that we are considering an undirected graph. Okay. Okay, so I can look at, for example, the lower triangular adjacency matrix because it is symmetric, so I don't need both parts of the matrix if I work with undirected graphs. Okay, and since the elements are 0, 1, it makes sense to assign Bernoulli distributions to this collection of 0, 1 elements. Okay, so I will assume that the components of this adjacency matrix are Bernoulli with probability pi distributed, where pi is a prior probability of edge inclusion. Okay. Okay, so if we assume that the elements are IID, Bernoulli pi, then the induced prior on the graph G is the product, okay, over all the elements in the lower triangular part of the matrix, which can be written in this form here, which is more or less a binomial, say, likelihood, okay, or something like that, up to the binomial coefficient at least, okay? So pi raised at the number of ones in the adjacency matrix, that is the number of edges in the graph that I call sites of G, times 1 minus pi, the number of possible the maximum number of possible one entries, which is q minus 1 over 2, okay, in the lower triangular part, minus the number of edges in the graph G. Okay. Okay, and this prior here requires to choose a prior probability of edge inclusion pi, okay, that you can set according to your prior knowledge about the sparsity of the graph. Okay, finally, if you don't want to rely on a fixed pi probability, you can also structure a hierarchical prior by assigning a prior on pi itself. Okay, and this is a prior which accounts for multiplicity correction, okay, in the Bayesian framework. Okay, so this is a hierarchical prior, okay, which is inspired by the literature on variable selection. The reference here is Scott and Berger, and that we can easily adapt to our graphical model context. So we start again by assuming that the elements of the lower adjacency matrix are Bernoulli pi, conditionally on pi. And then pi is a probability, right? So something between 0 and 1. We can assign to pi a beta prior, okay, with hyperparameters A and B. So instead of fixing pi, we add a level of hierarchy to our prior on the graph. Okay, it is possible to show that this induces a prior on the graph, a marginal prior on the graph that we can compute if we integrate out with respect to pi. Again, this is a marginal prior, okay, and which admits this kind of closed form expression, which is basically a ratio of normalizing constants of beta, say, prior and posterior densities, okay. Okay, so still in this case, we need to fix some hyperparameters, in particular A and B, the hyperparameters of the beta prior, in several possible ways. If we apply, if we set, sorry, A and B equal to 1, we know that a beta 1, 1 is a uniform, right? Okay, so this will imply that all values of pi are, let's say, equally likely, okay? And that the expected value of pi is 0.5. Okay? Otherwise, we may want to encourage, again, sparsity, and this can be achieved by choosing A smaller than B so that the expected prior probability of edge inclusion is smaller than 0.5. Okay, and so we should favor simpler graphs, okay? So graphs with a moderate or small number of edges. Okay, is it okay? Makes sense? Is it clear? Okay, so this is about the choice of priors for graphs, okay? Okay, so yes. Yes, it's or 0 or 1. Yes, 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 yes. It makes sense because I would say that it helps to decide whether there is or not an edge, okay? And you would like to avoid all the, let's say, intermediate settings, okay? So in a sense, you would like to reduce the uncertainty about the absence or presence, okay? I think it is a possible choice. Of course you can. It looks like an horseshoe prior, okay? Yes, 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 of course. I mean, any choice of A and B can lead to valid results. You can check and see what is the impact of the prior on your inference. What I expect if the sample size is limited is that under the choice that you suggest, you have something, you have posterior probabilities of edge inclusion. We will look at posterior probabilities of edge inclusion, which are more let's say, polarized, around 0 or 1 under that kind of choice of the prior hyperparameters. But it makes sense, of course. Okay, so if we have all these ingredients, then an MCMC algorithm over the space of graphs can be structured as follows. So we need to start from an initial graph, an arbitrary graph it should be. Let me call it G0. And then we need to fix a number of MCMC iterations, say capital T. Okay, and this algorithm will output a sample GT from approximate sample, say, from the posterior of G. Okay, so basically this consists of a loop, okay, which is iterated across T values, where at each step, let me call G the current graph, okay, or the graph at time T minus 1. What we need to do is to basically implement 3 steps. We need first to propose a new graph from our proposal distribution by applying one local move, okay, by insertion or deletion of an undirected edge, if you consider undirected graphs. Then we need to compute the probability of acceptance, the alpha, okay, in our Metropolis Hastings scheme. And then we need to decide whether to update the graph or not. So whether to set G at time T equal to the proposed graph, G prime, and this will occur with probability alpha. Otherwise, that is with probability 1 minus alpha, we will not accept the proposed graph, and the graph at time T, will be equal to the graph at time T minus 1. Okay, so we don't move in practice. Okay, we are still at GT minus 1. Okay, so if we iterate this procedure for a number of iterations, capital T, then we obtain a sample from an approximate posterior distribution over the space of graphs. Okay, is it okay? Okay, so before specializing everything to the Gaussian setting, let me mention how we can summarize this kind of output and then how we can do some posterior inference from this approximate posterior distribution. Okay, so the problem is that the output is a large number of graphs, okay, G1, G capital T, which have been visited by my Markov chain over the space of graphs. So we would like to summarize in some way this collection of graphs. So the first thing that we can do is to use this MCMC output to approximate a posterior distribution over the space of graphs. Okay. How can we estimate posterior probabilities of graphs? The idea is to use the MCMC frequencies of visits. Okay, so the number of times or the proportion of times any graph G is visited by the MCMC chain. Okay, so if capital T is the number of graphs in the MCMC chain, then 1 over T, the sum of indicator variables, 1 if G at time T is equal to the candidate graph G, will provide you an estimate of the posterior probability of graph G. Okay. Okay, where 1 is in an indicator function equal to 1 if GT is equal to G, 0 otherwise. Is it okay? Okay, moreover, we would like to have something which is a more synthetic summary. Okay, for example, we may be interested in computing the probability, in estimating the probability of inclusion of a specific link. Okay, in which case what we can focus on is a marginal posterior probability of edge inclusion. So let me consider, for example, an undirected edge, okay, between U and V. We would like to quantify the marginal posterior probability of inclusion. Okay, so with which probability we include there is an edge between U and V. So still we can use an estimator based on the proportion of times we observe this event in our MCMC output, and we can estimate this probability using 1 over t, the sum over all visited graphs of indicator functions that are 1 if graph at time t contains the undirected edge UV, 0 otherwise. Okay, so the proportion of times the visited graphs have an edge between U and V. Okay. Okay, and this will provide you, if you want, a collection of posterior probabilities of edge inclusion for all possible links. Okay, so something that you can organize in a matrix, okay, in a Q times Q matrix, where at coordinate UV you have the probability of inclusion for a link between U and V. Okay, we may also be interested in summarizing with a single graph estimate, starting from our posterior over the space of graphs. Here, the most common choices are two. The first one is based on what is called the maximum a posteriori graph model, which is the graph with the highest estimated posterior probability. Okay, so if you approximate posterior graph probabilities using this expression here, you may look at the graph with the highest posterior probability, and this is called maximum a posteriori. Otherwise, you can consider what is called a median probability graph model. The median probability model was introduced in the same paper that I mentioned before by Scott and Berger, where it was also shown to have optimal properties from a predictive point of view, so better than the maximum a posteriori in a linear model selection context. So again, here we can adapt it. Okay, so we can borrow ideas from linear models to graphical models, and we can construct this graph by computing first the probabilities of edge inclusion, posterior probabilities of edge inclusion, so P of UV given X, and then we can decide to insert an edge between U and V if this probability is greater than 0.5, okay, exactly in a median probability model estimate. Okay, so basically this is the graph containing a link between U and V if and only if the probability of inclusion of that link is greater than 50%. Okay, and we call this median probability graph DAG or UG model. Is it okay? Okay, so now we can specialize everything to Gaussian graphical models and both undirected graphs and directed acyclic graphs. Although the framework that I discussed till now is something that you can apply to, let's say, any kind of parametric graphical model, even categorical, or perhaps something with mixed data or something a bit more complex. Okay, so issue number one was how to design priors for graphical model comparison. Okay, so this is a problem that have received quite a lot of attention in the last at least 30 years. Okay, and the main difficulty in a Gaussian setting is that the parameter of interest, which is the precision matrix omega, is not just SPD, as we said a lot of time, but it must also satisfy the conditional dependencies imposed by the graph, which are 0 entries at some position. Okay. Okay, this is true for undirected graphs. It is true for a DAG if we look at the reparameterization in terms of B and D, okay, what we call the modified Cholesky this morning. Okay, so there are some works focusing on decomposable UG models, and in particular, this paper here by David and Lauritsen, 1993, who introduced a class of priors called hyper-Markov laws, which are a general class of priors for the parameter of a graphical model, which is Markov with respect to an undirected but decomposable graph. Okay, and this class of priors was specialized to Gaussian DAGs, leading to hyper Wishart priors or hyper inverse Wishart priors, which are an extension of the Wishart that we summarized this morning, or even to categorical DAGs through the so-called hyper Dirichlet prior. Okay, Dirichlet because a conjugate prior for the parameter of a categorical model is the Dirichlet distribution. Here you have a hyper Dirichlet because you have something which is, say, more general, more complex, but still based on Dirichlet type priors, okay? Because the parameters are probabilities to which you can assume Dirichlet type priors. Okay, but much more recently, or a bit more recently, Alberto Roverato introduced the G-Wishart prior, which is actually a generalization of the hyper Wishart prior to any kind of undirected graph model. So also to non-decomposable graphs. And this is what I would like to discuss a bit today, okay, since it is a more general prior. Okay, so this is what you can do for with undirected graphs. While for DAG models, there are even for DAG models there are many possible solutions to this issue. There are a couple of works by Eckermann and Geiger who propose methods to assign priors for the parameters of categorical and Gaussian DAG models, which in practice does not require to set a Markov type prior. So a prior, an explicit prior distribution on omega or the parameter of a categorical graph, but basically they rely on a set of general assumptions showing that if these assumptions are satisfied by the model, say the likelihood, and the prior that you would like to have, then you can directly compute a score, a marginal likelihood, using a closed form expression. Okay, and these scores are specialized to categorical data through the so-called Bayesian Dirichlet equivalent score, and to Gaussian DAGs through the so-called Bayesian Gaussian equivalent score. Okay, equivalent stands for the fact that they guarantee Markov equivalence, so they guarantee score equivalence between Markov equivalent DAGs, which is one of the requirements that we mentioned this morning. Okay, so they are scores, so you can even implement these scores within an MCMC procedure as the one showed before, or even in an optimization procedure like the hill climbing method, okay? If you want to be frequentist, but you want to use a Bayesian score. Okay, however, more recently, Cao and co-authors, 2019, introduced an explicit Wishart type prior for the parameters of a Gaussian DAG model, which is called the DAG Wishart. So an extension of the Wishart distribution to DAG constrained covariance matrices or their reparameterizations. And this is what I would like to discuss with you. Okay, so let's start from Gaussian undirected graphical models and our definition of Gaussian UG model. So we have an undirected graph, G. Okay, and we assume under G that the joint of x1, xq, given omega, our precision matrix, is multivariate normal, with omega satisfying the Markov property of the undirected graph G. Okay. Okay, remember what we said this morning. If there is a missing edge between U and V, that is UV does not belong to the set of edges E, then the entry at position UV in omega is equal to 0, okay? Meaning that XU and XV are independent given the rest. Okay, so this is exactly the type of constraint that our G-Wishart prior must satisfy. 0 elements at the right position depending on the structure of the graph. Okay, so if we are in this multivariate Gaussian setting, we can write a likelihood function, okay, which has this form here, as we brought this morning. Okay, and in particular, it is proportional to the determinant of omega, exp minus 1/2, the trace of omega s, where s is our sample matrix X prime X. Okay, now we would like to assign a prior to omega, possibly a conjugate prior, so something which will lead to a posterior which is of the same family. Okay, so something which should have a structure which is more or less the same of this likelihood here. Okay, this is the reason why I wrote it explicitly. Okay, so a conjugate prior for omega, which is Markov with respect to an undirected graph, is the so-called G-Wishart distribution, WG, where G emphasizes that this prior is not on a precision matrix, is not just on the precision matrix SPD, but also Markov with respect to a graph G. Okay, so basically you have an extra parameter in the distribution. Okay, so we say that omega is a G-Wishart distribution if its probability density function can be written in this form here. Okay, where what we have basically is a kernel which is very similar to the kernel of a Wishart distribution. If you remember, the determinant of omega raised at something, our exponential kernel. And then we have something before, which is the normalizing constant, okay, that we can write as 1 over I of G, B, and D. And this distribution depends on two parameters. The first one is a degree of freedom parameter, B, which is a scalar. The other one is a matrix, D, which is instead a symmetric definite positive matrix. Okay, so exactly as the Wishart distribution. Okay. Okay, so and here we start with issues for this prior because we have a normalizing constant, okay, which we can write as an integral, okay, of the kernel of the distribution integrated with respect to omega. The main difficulty is that we cannot compute exactly this integral here, okay. The reason is that the integral is not over the space of SPD matrices, but it is over the space of SPD matrices that are also Markov with respect to the graph G. Okay, so we cannot provide a closed form expression for this normalizing constant, and in turn, we cannot provide a closed form expression for the marginal likelihood, as we did instead this morning using a standard Wishart prior. Okay, so accordingly, we will need to approximate this normalizing constant in some way. Okay, but there are still some good properties of this prior, of course, okay? It is not difficult to show that this is conjugate because if you combine the prior with the likelihood, okay, you see that basically they have the same factorization, they have the same structure. So the posterior distribution is still G-Wishart. Okay, so omega given X is still G-Wishart with updated parameters, which are B plus N, where N is the sample size, okay, and D plus S, where S is our X prime X matrix. Okay, so this is a conjugate prior. Second, the marginal likelihood can be written in principle as a ratio of prior and posterior normalizing constants still, up to this term here, coming from, as usual, the likelihood function. The only problem is that we cannot evaluate analytically the two normalizing constants, okay? Is it okay? Okay, and I emphasize the dependence on the graph because both in the likelihood and the prior here, something that I did not before, just for simplicity, because now I care about the graph because I'm interested in a posterior over the space of graphs. Okay, so the graph matters, of course. Okay, so the main issue now is that we don't have an explicit form for this normalizing constant because there is no explicit solution for the integral that we wrote before. Actually, there is only if the graph is decomposable. Okay, and this is exactly what is also reported in the paper by David and Lauritsen that I mentioned before. So if the graph is decomposable, okay, we can compute it analytically, and then we can go back to our MCMC scheme. We can compute the marginal likelihood, and we can run our MCMC scheme. But if we want to consider more general undirected graphs, there is no, in general, analytical solution. So we need to approximate this normalizing constant. And here there are several possible contributions in this direction. For example, Monte Carlo approximations, this paper by Helen Massam and co-authors. There are Laplace approximations provided by Dobra and Lenkonsky. There are also methodologies, this paper here by Wang and Li, who proposed an approach which basically avoids the computation of the normalizing constant if you consider in your Metropolis Hastings ratio two adjacent graphs. Okay, it can be shown that the normalizing constants simplify in such a way that you just need the normalizing constant of an inverse Wisher distribution, which instead is available in closed form, as we wrote this morning. Okay, more recently it was proposed a closed form but still approximation of the ratio. Okay, so sorry for the technical issue. If you can provide an approximation based on one of the strategies that I reported here, then what you can do is to implement your MCMC algorithm for structured learning of UG models. Okay. The only difference is that you need to approximate the marginal likelihood because you cannot compute it analytically. Okay, so in order to introduce one of these approaches to UG model selection, let me first the more general scheme. So this is not working anymore. Okay, it was an algorithm to approximate a posterior distribution over the space of graphs. Okay, so we were not interested in inference on the parameter, what we called omega, right? The precision matrix. And so we integrated out omega. Okay, alternatively, what we can consider is a joint posterior over the space of graphs and precision matrices, okay? Instead of integrating out omega. Okay, so this is possible, okay? In which case, what we would like to approximate is a joint posterior over the space of omega and G, okay? Which can be written as the product of three terms in this case. The first one is the likelihood function, so not an integrated function, in integrated likelihood anymore. The second one is the prior on omega given the graph, and the last one is the prior on the graph itself. Okay. Now the main problem in okay, the main problem is that we have two parameters which depend each other. And in particular, the support of omega depends on the support of G. Okay, so if you change the graph, basically you change the constraints that you impose to omega, right? Okay, so you cannot use a standard MCMC method in this case, but you need to rely to something which is, let's say, a bit more complex. For example, a reversible jump algorithm, for those of you who are familiar with this kind of algorithms, or something which was proposed by Mohammadi and Witt, and which is implemented in the package that we will discuss later on, which is instead based on a birth-death MCMC algorithm. Okay? There are other proposals, of course, in the literature. Okay, so let me just give you some information very briefly about the properties of the algorithm, which is provided by Mohammadi and Witt, because it is the one that we will use in our R session. So the main features of this algorithm are that it is based on a Markov process, okay, which, as before, explores the space of graphs by considering adding and removals, addition and removals of edges, okay, which correspond to what is called, according to their notation, to birth and death events, okay? Then the idea that he implements is that the time between the birth and death events are modeled through a Poisson process with some rate parameter, and they show that the time between two consecutive birth and death events has an exponential distribution. So basically the idea is that in their algorithm, they propose a move, they accept this move, but the weight that they assign to that move, which can be the addition of an edge or the removal of an edge, the birth and death respectively, is given by a probability okay, corresponding to the birth or death events, okay? So this posterior probability is approximated through a probability corresponding to a Poisson process for which they provide an expression in their paper. Okay, so the output of this algorithm is a posterior distribution, which is not on the collapsed space of graphs, but on the joint space of graphs and precision matrices. So from this algorithm, we can also provide inference on omega itself, okay? Still, the algorithm is based on two steps. The first one is the update of the graph, okay? So the update of G. While in the second step, conditionally on G, we can update omega, okay? How? By sampling from its posterior distribution, which is still G Wishart, okay? We don't have closed form expression for the normalizing constant. We need to approximate something again, okay? But the idea is to approximate draws from this posterior distribution using one of the approaches that we mentioned before. And in particular, the one which is implemented in the package was this proposal by Lenkonsky in 2013, okay? Okay, so basically there are two steps that are iterated sequentially, the update of the graph and the update of omega conditionally on the graph, okay? Okay, so let me show you some R code, which is provided in this R script session 3, Bayesian methods. Okay, so in order to apply the method by Mohammadi and Vit, we need their package, which is called BDGraph. Okay, and let me exemplify this using the simulated data that we generated this morning, okay, with our very simple example. Okay. So the MCMC for undirected graph structural learning is provided in the package BDGraph, okay, under the function whose name is BDGraph itself, which have 4 main arguments. The first one is the data matrix, okay, called data, the NQ data matrix. The second one actually is a method, okay, that we can set according to the type of data that we have, okay? We may have Gaussian data, we may have other kind of data, for example, mixed data, okay, in which case there are other methods that are implemented. So in our context, we need to set method equal to GGM, which stands for Gaussian graphical model, okay? So it will consider a G Wishart prior and the scheme that we mentioned before. Okay, so finally, since this is an MCMC method, we need to set the number of iterations and the burn-in period, iter and burn-in respectively. Okay, so let me fix, for example, 6,000 and 1,000 respectively. Okay. We can run it. And then we can look at the posterior summaries which are provided by the method. Okay, so there is a summary method which applies to an object of class BDGraph, like our output here. Okay, and among the outputs provided by the package, we have what is called selected graph, which is exactly the median probability graph model. So the graph that you obtain by including an edge between U and V whenever the estimated posterior probability of inclusion is greater than 0.5, okay? And this is the result that we obtain on our data. Okay, moreover, we have something more, because remember what I told you is that we also have inference on the precision matrix. Here the precision matrix is called capital K, okay? And K hat stands for the posterior mean, the posterior expectation of our precision matrix, okay? Which is reported here as a Q times Q matrix. Okay, then you have also the probabilities of edge inclusion, P links, they are called, okay? So the probability of an undirected edge between 1 and 2, and so on. Whenever this is greater than 0.5, you will have an undirected edge in your selected graph here, okay? Okay, so this is the output, say, the main outputs that are provided by the package bdgraph. Okay, so we can move to directed acyclic graphs instead, and then considering a Gaussian DAG model. Okay, so the starting point is as usual our DAG D, and we will assume that X given omega is multivariate normal with omega satisfying the constraints imposed by a DAG this type. Okay, so now we need to recall what we called the structural equation model representation of a Gaussian DAG model, which, if you remember, is based on a reparameterization in terms of a matrix of regression coefficients, capital B, and a diagonal matrix D collecting node conditional variances. Okay, the reason is that even in Bayesian inference, it is easier to structure a prior on these two parameters because we know exactly what are the constraints imposed by the graph on the B matrix, the 0 entries in B, rather than in omega for a DAG. Okay, so just to ease the notation, let me call capital L I minus B so that we can write our structural equation model as L prime X equal to epsilon, where bold X is our q-dimensional vector, x1, xq, while epsilon is our q-dimensional vector with the error terms, the one which has a multivariate normal q distribution with diagonal variance covariance capital D. Okay, so still in L, we can read exactly the constraints imposed by the DAG, because the UV element of L will be different from 0 if and only if we have an edge from U to V, while the diagonal elements of L are by definition equal to 1 since L is I minus B. Okay, so now we have all the diagonal entries 1 and the out diagonal entries that are different from 0 only if there is an edge between U and V, or to be more precise, from U to V. Okay, still we can express a relationship between omega and dl, which is called modified Cholesky decomposition, okay, and which is given by the expression here. So if you apply the variance operator to x, for example, here, and then you compute from the variance covariance matrix the inverse, that is omega, then you obtain this kind of expression, which establishes the relationship between LD and omega. Okay, so a prior for DAG model comparison can be assigned to LD rather than to omega. Okay, and such prior is called the DAG Wishart. Okay, so let me just fix a bit more of notation, which is the original one provided by Cao et al. In their paper, although it is not probably the best notation that one can conceive, but it is the original one. So I will need to select elements in the L matrix corresponding to the parents of node J. So I will use this notation to index rows corresponding to the parents of J and column corresponding to J. Okay, so this will index the elements in column J corresponding to the parents of node J in the DAG. Okay. Okay, so that L with this subscript here will be the corresponding submatrix, which in practice is a subvector, if you like. Okay, so if we write node by node our SEM representation for our Gaussian DAG model, that we end up with this system of linear equations where xj is a linear function of its parents, okay, so L prime x parents, plus an error term, epsilon j, which has a univariate normal distribution, zero mean, and conditional variance djj. Okay, so again, we have a system of normal linear regression models, and we know how to do things with normal linear regressions. For example, we know how to write a likelihood function. So if you remember the DAG factorization, which is the factorization over nodes, then this can be written under this parameterization as a product of normal densities for xj given a linear predictor, which is minus L prime x parents j, and conditional variance djj. Okay, so which is just another way to write the DAG factorization under the Gaussian assumption using this kind of parameterization. Okay, if we now assume to have our data, so n observations, each is q variate, okay, xi, then what we can write is a likelihood function, which would be a product I1 to n of f xi1 xiq, and that we can write in this form here. And then let me stress that within parentheses here, what we have is the likelihood of a normal linear regression model. Okay. Looks okay? Is it okay? Makes sense? Okay. Okay, so let me just give you a brief example just to understand this kind of notation. Here we have a 3-node DAG, okay, with 3 random variables, x1, x2, x3. Okay, so we have our random vector x, and then we have a graph which is fully connected with these edges from 3 to 2, 3 to 1, 2 to 1. So the corresponding elements in L will be non-zero. Okay, so in practice you have a coefficient from 2 to 1, from 3 to 1, from 3 to 2. Okay? Then the diagonal elements equal to 1, and then all the other elements equal to 0. Okay. And then we have the error term, which is epsilon 1, epsilon 2, epsilon 3. Okay, so that we can write our structural equation model as L prime x equal to epsilon if we want to use matrix notation. Otherwise, we can write explicitly the set of linear equations, one for each variable, x1, x2, x3, okay, which will have this form here, okay, that you can see very similar to the linear equation in a linear regression model, right? Where the parents basically play the role of the covariates for each node. Okay, so this implies that the distribution of each node is normal, the conditional distribution, with some regression coefficients, some, say, parent nodes playing the role of the covariates, and some conditional variance. Okay. Okay, then the issue is the same as before. We would like to assign a prior on the parameter of a Gaussian DAG model, which satisfies the constraints imposed by the DAG. Okay, and this is not enough. We must be careful because with DAGs, we must care about Markov equivalence. We would like this prior to satisfy an important requirement. The DAGs that are Markov equivalent must be scored equally. They must have the same score, which in a Bayesian framework is the marginal likelihood. Okay, so a prior on omega can be assigned through a prior on its reparameterization into DL through a DAG-Wishart prior, okay? The DAG-Wishart prior is defined, it's based on 2 hyperparameters, which are an SPD matrix, capital U, okay, which is a position hyperparameter, and a vector of shape hyperparameters, A of D, with components, 1 component for each node. Okay, and the kernel of the distribution is the one that I reported here, okay, where you can recognize again that there is an exponential kernel, which is 1/2 the trace of something which multiplies U. And this something here is nothing but the decomposition of omega. Okay, so the same kernel of our likelihood, omega times something, okay, which suggests again that this prior is conjugate. So if we combine this with the likelihood, what we obtain is a posterior which has the same kind of structure, so it is still DAG-Wishart. Not only, a property of this prior is that the node parameters, okay, so let's say the regression coefficients and conditional variance of node variable j are a priori independent, so that you can factorize your prior on DL as a product over j. Okay? And the nice thing is that the induced prior on Lj and Djj is a normal inverse gamma prior. Okay? So the elements of Lj are jointly multivariate normal distributed with some mean vector and covariance matrix, while the element djj has an inverse gamma distribution, okay? So forget about the parameters, but remember what I told you this morning. If we have a normal likelihood, okay, for a linear regression model, we have a multivariate normal inverse gamma prior, then we have conjugacy, and we have the posterior in closed form, the marginal likelihood in closed form. Here, the only difference is that you are considering Q linear regression models, each with its own conjugate normal inverse gamma prior, but which are conjugate, and so which allows to compute posterior and marginal likelihoods in closed form expressions. Okay, so these priors depends on several hyperparameters, okay, U and A in particular, that we need to set, that we can set according to our prior knowledge or whatever, but importantly, we must set in such a way that we guarantee score equivalence, that is, Markov equivalent DAGs leading to the same marginal likelihood. So we are not free to choose any value for A and U. One choice guaranteeing score equivalence is the one introduced by Consonni and Peluso in this paper 2020, okay? While a standard choice for U, this is a choice basically only on the A parameter of the distribution, so whatever U is. For U, what we can do is, for example, to set it as a diagonal matrix, which will reflect a prior belief of marginal independence between components. Otherwise, we can multiply by constant G if we want to control for informativeness of the prior, okay, and making the prior weakly or more informative, depending on what you need. Okay, so a couple of nice implications that we mentioned before. This prior is conjugate, okay? The intuition is that the Dag-Wishart can be written as a node-by-node factorization as the likelihood function, okay? And in each component of the factorization, we have a normal likelihood and normal inverse gamma priors, which are conjugate. So the posterior of dj Lj is still inverse gamma and multivariate normal with some posterior hyperparameters that we can call A tilde U tilde, which are nothing but the prior hyperparameter plus the sample size, as in the Wishart that we saw this morning. U, the prior hyperparameter of the Dag-Wishart, the shape hyperparameter, plus the X prime X matrix. Okay, so we know how to sample from inverse gamma and multivariate normal distributions, or at least there are packages to do this. So implicitly, we can sample from Dag-Wishart posterior distributions if we want to do inference on the parameters of a Gaussian Dag model. Last, to implement an MCMC scheme for Dag model selection, we need the marginal likelihood, right? We need to integrate out the parameters, which are L and D. Okay, so we would like to compute an integral of this form here, the marginal likelihood of the Dag D. Okay, so now if we write both the likelihood function and the prior using the node-by-node factorization that we wrote before, so the product J1 to Q, we will end up with this kind of expression, okay, where each term, J, again, is a product I1 to N of normal distributions, normal densities, times a prior of this form here, which is a multivariate normal inverse gamma prior. Okay, so we can work separately on each component J, okay, of our marginal likelihood and compute the marginal likelihood relative to node J using the same results that we would use for normal linear regression. Okay, and we will end up with this marginal likelihood here, which is again nothing but the marginal likelihood of a normal linear regression model, the one that we can wrote as the ratio of prior and posterior normalizing constants. And this is possible because of properties of the Dag-Wishart and because of conjugacy of normal inverse gamma priors with normal densities, or with the density of a normal linear regression model. Okay, so finally we have a closed form expression for each term, for each marginal likelihood, okay, which if you want to write explicitly as the ratio of prior and posterior normalizing constants has this expression here. Okay, you can forget about it. The message is that we can evaluate it analytically. Okay, so again, if you have data, if you have a prior, you can compute it exactly. And this will give you an exact form for the marginal likelihood of DAG D. The ingredient that, if put within your MCMC scheme, will allow you for structural learning of DAGs. Okay, any question, any curiosity? I mean, besides the, let's say, more technical results, but is it clear? Okay, yes. Yes. Of course, there is a strict connection between, but even between Bayesian linear regression and lasso, say, regression. Just because the actually the connection is more with ridge regression. You know, the ridge regression is equivalent to a Bayesian linear regression, okay? Because the shrinkage can be expressed through a prior on the elements of the beta regression coefficients. So of course there is a connection even with the lasso, in the sense that in the lasso you shrinkage by putting a penalty, okay, depending on lambda. Here the effect of the penalty is in the prior, of course, okay? So for example, if you center your prior on L with a zero mean, okay, and then you control for the variance of this prior, basically what you are doing is a shrinkage to zero, okay? Now, if the question is, what is the relationship with instead the graphical lasso, which is instead based on an undirected graph approach, while here we are doing with DAX, I don't have an answer, a precise answer. But of course, there are connections between the two approaches. In both cases, you are, in a sense, encouraging zeros by doing some kind of shrinkage. In one case, the shrinkage is explicit because you add the penalty and the tuning parameter. In this case, it is implicit in the Bayesian approach because you have the prior. And depending on the prior hyperparameters, you can control for, let's say, the shrinkage, okay? Yes, 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 of course. No. This is an important difference. So here we are reasoning conditionally on a DAG. So given the DAG, we have an exact factorization. In the graphical lasso, you say, okay, I don't assume a known graph. Okay, I translate the problem into a problem of a collection of node-wise regressions, but whatever the graph is, and I encourage elements to be equal to zero. In this case, we are reasoning conditionally on a DAG. So we have an exact factorization with respect to a given DAG. Then we will move the DAG and then we will do structured learning, but okay, other questions? Yes. So you would like to avoid cycles? Okay. Okay, so again, here we are reasoning conditionally on a DAG. So the DAG itself avoids cycles, okay? So we are considering a fixed DAG, which is acyclic by definition. And under a DAG, we can specify this kind of prior. We have these results here. We introduced the structural learning in our MCMC. When we move the DAG, we change the DAG by addition, removal, or reversal of edges, provided that what we obtain is a DAG. We compute the score of the DAG, the marginal likelihood, and then we accept or reject it according to the Metropolis-Hastings ratio. So in that step, you need to guarantee acyclicity by checking if what you propose in your proposal distribution is acyclic. You mean the ordering of the nodes or something like that? There is no need to know. Oh, no, okay, okay. No, this is something that I didn't make. Okay, you can remove an edge from U to V, and then you can add an edge from V to U. In which case you change the topology of your DAG. Otherwise, you can consider other moves, for example, the reversal of an edge. Okay, in which case you change the ordering as well. You agree? So basically, you need to avoid cycles. And the way in which you avoid cycles is to check if what you propose is a DAG, so it is a cyclic or not. So you discard graphs having cycles, but this is only in the proposal distribution. Then whatever we did here is conditionally on a DAG, which by definition is a cyclic. Sorry, can you repeat? The running time? Okay, so this is another point. It depends on how many iterations you need. I think it scales linearly in the number of, I don't know, observations, in the number of variables. I don't know exactly. It may require, of course, much more time if you want to explore a space which is huge. It is. Okay. Okay, so you may need, of course, you may need much more time to reach, say, convergence if you have a huge number of variables. That's for sure. Okay, but let me say that in general, all these methods here for Bayesian structural learning are not performing very well if you have high dimensional context. There are other types of priors that you can structure. For example, based on shrinkage. Okay, one possibility, if you consider, for example, UG estimation, undirected graphs, what you can do is instead of assigning a prior on omega, you can work element by element on the elements of omega and use some kind of shrinkage prior. For example, spike and slab or horseshoe priors, okay, provided that the prior that you obtain on the omega matrix is Markov with respect to a graph. So instead of assigning a prior to the whole matrix omega, you work element by element and you encourage elements of omega to be 0 or not 0, okay, based on a shrinkage type prior like spike and slab. Okay, so this kind of approach is, of course, much more efficient in high dimensional context, okay, because you are not working on the space of graphs, but it's like saying, okay, I assume that the graph is complete. There are all possible connections. I want to encourage connections to be absent or present using a shrinkage type prior. Okay, so you avoid to explore the space of graphs. There is one complete graph, and then you shrinkage the elements of omega to 0 or not, okay, based on the evidence that you have. Okay. Other questions? Okay, so we can have a look at some R implementation of the MCMC scheme for DAG model selection that I tried to summarize before. This is provided in a package called BCDAG, which stands for, probably I have one slide more, which is called Bayesian Structure and Causal Learning of Gaussian Directed Graphs. In particular, an MCMC algorithm for DAG structure learning is provided by a function called learnDAG under a setting which is collapse equal to true, which means I don't want to do inference on the parameter D and L. I want to collapse on the space of DAGs only. Okay, if you want to do inference on the parameters of the DAG, D and L, and implicitly on omega, you can set collapse false, in which case the algorithm will approximate a joint posterior over DAG, D, and L. Okay. Okay, so other inputs of the function are the data matrix, as usual, the number of MCMC iterations and the burn-in period. And then we need to set the hyperparameters of the DAG-Wishart prior, A and U. And finally, a prior probability of edge inclusion, what we called pi in our notation before. It's called W here in the R implementation. Okay, so let me show you briefly how we can do structured learning of DAGs using the learnDAG environment. Okay, so I will start by setting the hyperparameters of the DAG-Wishart prior as A equal to Q, okay, which is a sort of default value. It must be strictly greater than Q minus 1, okay, the value of A, while I will set U as a diagonal matrix with 1 entries on the main diagonal. Okay, next, the number of MCMC iterations, for example, 6,000 iterations, and I will include a burn-in period of 1,000. So the first 1,000 rows will be discarded because they may be too far from the kernel of the posterior distribution. Okay, and so we can run our learnDAG function, which is sampling some DAGs approximately from the posterior distribution over the DAG space. Okay, so we would like to summarize this posterior distribution over a space which is quite complex. It is a space of DAGs. We can use a couple of functions, a couple of methods that are available. The first one is a summary method. The second one is a plot method, okay? So if you apply summary to an object of class learnDAG, what you obtain is the following. We have information, for example, about the kind of output that we have. This is a collapsed sample from the posterior distribution of DAGs, okay? Okay, then we have a summary of the prior hyperparameters, prior probability of edge inclusion that I fixed at 0.1, and the hyperparameters of the Wishart that I set. And then we have the estimated posterior probabilities of edge inclusion, saying that, for example, there is a directed edge from 2 to 1 with probability 0.48, okay, or between 3 and 1 with probability 0.6 or whatever, okay. Okay, if instead you use the method plot, what you will obtain is a list of outputs. The first one is the median probability DAG model. Okay, so the DAG model containing an edge between U and V if the corresponding probability of inclusion is greater than 0.5. And we end up with this DAG estimate. Okay, the second one is just a graphical representation of the posterior probabilities of edge inclusion, which is provided in this heat map, okay, where the UV component correspond to the posterior probability of an edge from U to V, okay? So it's just a graphical representation of the matrix here. And I think we have something more. Okay, so for example, the distribution of the DAGs sites. So the number of edges in the DAGs visited by the Markov chain, okay, which is something around 5 and 6 in this example. And I think that's all. Okay, any question, any curiosity? Yes. Yes. This is a good point. I would say that yes, I would say that in principle, no, there is no guarantee. Okay, so we should check. In practice, I never obtained anything which was not a DAG for some reason. Yes, and then what I would say also is that if you want to summarize with something which is interpretable, again, from this DAG estimate, you should reconstruct the representative CP DAG or essential graph. Okay, so there may be other DAGs which have the same estimated probability because they are Markov equivalent. So again, you can convert the estimated DAG into an essential graph. Okay, so if you are interested in checking for conditional independencies, but of course they are all equivalent. Okay, so you can consider any DAG in the Markov equivalence class of this DAG here. Okay, any other question? Okay, so let me just give you some references. Okay, so the R implementation of the MCMC for DAG structural learning in the BC DAG environment is summarized in this archive paper, co-authored by Alessandro Mascaro, who is there. So if you have questions, you can ask to Alessandro, who is the main responsible of many things that are within the package that I showed you. The second reference is about the hyper Markov laws for the analysis of decomposable graphical models, if you are interested in this topic, which are specialized to both categorical and Gaussian data. Then the algorithm, the birth and death algorithm by Mohammadi and Witt was introduced in this paper here. Okay, and there is also the Journal of Statistical Software paper for the R implementation in the BD graph package. If you like DAGs, there is the paper by Peluso and Consonni about the compatible DAG-Wishart prior, while for the G-Wishart prior, the reference is the paper by Roverato 2002. Okay, so if there are no other questions, I think we can stop here for our break, and then we will see for the next session, which will be the practical one. So I will provide you a data set and I will ask you to perform some analysis, and then we will discuss together the results that you obtain. Okay, so see you later.